So towards the end of today's class, I would like to talk about the exam that I handed back, as well as the rest of the course and what is that we'll be doing. Like, for example, about your second project, upcoming mini project. We'll talk about all that probably around like 6:40, 6:45. Okay, now let's get started with the next topic in our lineup, which is Laplace transforms, which is a very common and very powerful technique for solving linear ordinary differential equations in the form of initial value problems. And when we say initial value problems, the word initial should give it away for you. What we are talking about is equations in the time domain, dy over dt, or some derivative with respect to time, which is given to us as a ODE. Okay, equations of this form. So Laplace transform is specifically designed to reduce any time domain problem, a time domain ODE, into an algebraic problem, and then solve it algebraically to then extract the solution for the original initial value problem. And I'm pretty sure for all of you or most of you, you have already seen this before in some class. Can you tell me in which class you've seen this? System dynamics. Whenever you are studying the time response of systems or dynamics like response of objects that are responding to forces, any other place, any electrical engineers in the mix or somebody who've done circuits, control systems, circuit analysis, wherever you have equations which have a time dependence and then you are given an initial condition, your ultimate goal is to calculate y of t. That is where Laplace transform is actually useful. Okay, it's actually useful as well as one of the most intuitive, simple techniques that we can use. Or in other words, in this course, it's one of the lightweight topics. And module 3, which includes, the exam 3, which is going to include Laplace transform as well as vector calculus, would be one of the easier exams in the course because we have sort of crossed the peak in terms of the complexity of the topics, which was PDEs. So this should be something of a relief and let you focus more on the project work. This should be something you should be able to do relatively easy. Okay, so we'll start with the definition of what is Laplace transform. The Laplace transform is one of many. Laplace transform is a particular type of integral transform, or one of the integral transforms possible. And if f of t is a real value function of time, which we'll denote by t. So we'll reserve the symbol t only to denote time and not any other quantity in this chapter. And obviously, if it's time, it can only be positive. Then the Laplace transform is defined as, we'll write it uppercase F of S equal to 0 to infinity e power minus st f of t dt, where S is a parameter which is always positive. Okay, and we also give the symbol, at least the book gives the symbol L of F, Laplace transform of F. So this integration, as you can see, is done over the time domain from t equal to 0 to infinity. So this, most importantly, removes all time dependence and yields a function of S, the parameter S. It's a definite integral e power minus st times f of t, provided this product, this integrand is analytic, this integral will always converge. Okay. So just to start with an example, let's say f of t equal to 1. What will f of s be? That will be 0 to infinity e power minus st dt, or e power n minus st times 1 times dt, which is e power minus st divided by minus s from 0 to infinity, or 1 over s. I'm sure you know all this, like just trying to quickly summarize what you know, and then we'll start moving forward. Okay. If f of t is a function, let's say an exponential function, e power at, then f of s is 0 to infinity e power minus st e power at dt, or this is 1 over s minus k. I did skip a step there, but I'm sure you won't mind. Think. So this operation here, when I say the Laplace transform of a function f of t, this operation is linear with respect to f of t. This is linear with respect to f of t. Or in other words, what I mean is the Laplace transform of a combination of two functions can be written as a times the Laplace transform of f plus b times the Laplace transform of g. Actually, the book wants to use the symbol f. You would agree with me? This property, does it look obvious to you? The linearity property? All you have to do is wherever f of t appears, substitute a f of t plus b g of t, and this integral just becomes two integrals which are sum of each, and you will get this property. Okay, so it's a linear operator. That's the takeaway. Laplace transform is a linear operation. We already saw the transform of e power at is s minus a. So I can write Laplace transform of e power at is 1 over s minus a, which implies the transform of e power minus at would be 1 over s plus a. Replacing a with minus a, I would get s plus a. Right? The whole thing about Laplace is not doing the integration, but using a table of integrals to quickly get what you need. Okay? It's not about, I know we can all do the integration, and given time you can do integration by parts and everything, but it's about using the table which you can easily construct for each function, and the table that's going to be your best friend is table 6.1. In the exam, I will provide that table along with the question sheet. Okay, so you should know how to use it. So if I ask you what is the Laplace transform of, let's say, sine h, hyperbolic sine of at, this would be the transform of e power at minus the transform of e power minus at, which is 1 over s minus a minus 1 over s plus a. So that would be what? 2a divided by s squared minus a squared. Okay? No, 2s. No, yeah, 2a. Sorry, I forgot a 1 by 2. So there will be a 1 by 2 here. So this will be 1 by 2. So this will be a. And you can do this for cos h. You can do this for many other functions. So if you go to table 6.1, you are given examples or integrals, Laplace transforms of various common functions. Like for example, if you want the Laplace transform of t power n, what will you do? That is 0 to infinity e power minus st t power n dt. We will do integration by parts, right? Where n is some non-negative integer. If n is some non-negative integer. You'll do integration by parts, which you can do. And again, I'm telling you, my intention is not to test you on your integration skills. So this result, I trust that you would be able to do. So I'm just going to tell you, the answer is n factorial divided by n factorial divided by s power n plus 1. I just took it from the table. Okay. So we come to our first kind of useful result, which is called the first shifting theorem. First shifting theorem. Okay. Which goes as, if I want to know what is the Laplace transform of a function, which is e power at some multiplied by some function of time. What is this result? If Laplace transform of f of t is known to be, let's say, f of s, then the Laplace transform of e power at times f of t is simply 1 over f of, is simply f of s minus a, which is whatever f of s is, wherever s appears, replace it with s minus a. So by that logic, can you quickly compute what is the transform of sine omega t? You can compute or you can look up. Sorry? Omega by s squared minus omega squared. Right? So he's saying it, you can check it, it's correct. Okay. So if you want the Laplace transform of e power at times sine omega t, that is simply omega divided by s minus a squared minus omega. So what is the lesson here? What can we take away from this shifting here? You will always be presented with a initial value problem, basically a time domain ODE with an initial condition. When you are doing Laplace transforms, the goal is not to do the integration each time, but to reduce that integral or transform to this template so that you can skip one step and go. If suppose some function g of t is what you are, suppose y of t is e power at times f of t. If you could write it like this, you are skipping one step by using the shifting theorem. Maybe f of t is already tabulated, it's a known function, it's just multiplied with an exponential. So wherever possible, you should look to use these results. Okay? Yeah, it should be plus x squared or plus omega squared. But the rest of the things remain the same. Wherever s appears, replace it with s minus k. So I'll write it wherever s appears in f of s, replace s with s minus a. So using this shifting theorem, what you want to do is go through problem set 6.1, which are functions of different types, and use try getting the Laplace transform of those functions. Okay, so problem set 6.1, I would suggest problems, actually all the problems. It's essentially basics. We'll try one example. Okay. Let's try problem. Let's try problem 16. So problem set 6.1, problem 16. The waveform in time domain is given like this. So this is some y of t, or f of t. The function goes from 0 to 1 in a straight line. And then goes from 1 to 0 in a straight line at time 2. And beyond time 2, the function just remains at 0. So if you were to write this as a piecewise function, f of t, where time is greater than 0, is this is what is the value here? T times the slope is 1, or just f equal to t. This is t. This would be 1 minus t, right? No, 2 minus t. 2 minus t. So for 0 less than t less than 1, and 2 minus t for 1 less than t less than 2, and 0 for t greater than 2. Before we launch into this, we would collect one result from here. What is the Laplace transform of t power 1, or just t? Laplace transform of t would be 1 over s squared. 1 over s squared. Okay, let's remember that. 1 over s squared. So f of s, which is the Laplace transform 0 to infinity e power minus st f of t dt. So this will be 0 to 1 e power minus st times t dt. plus 1 to 2 e power minus st times 2 minus t dt plus 2 to infinity e power minus st times 0 dt. That's a catch. This result is valid for 0 to infinity. Okay, so this integration is not for the from 0 to infinity. It's for a finite interval. So you'll have to use it carefully. Okay, so which you can do by parts. So this would be um, upper limit is minus e power minus s, lower limit is 0 plus 1 over s times e power minus st divided by minus s 0 to 1 plus minus 2 to s e power minus 2s minus e power minus s. Then you have to again integrate that. One goes away. This is plus, this is minus. So I have minus 1 over s squared or 1 over s squared 1 minus e power minus s. So this cancels away. 2 over s, 2 over s, e power minus 2s, e power minus 2s, minus plus, that goes away, plus, that is minus, so plus 1 over s, e power minus s, minus e power minus s. This is just getting some practice in doing the Laplace transform. Our original stated goal is still to use Laplace transform to solve ODEs, right? So which means we'll have to know how to take the transforms of a derivative because that's what appears in a ODE. dy dt, d squared y by dt, and so on. So is this okay? Did I make some mistake? I think it's okay. Suppose we are interested in the Laplace transform of f dash of t. What would that be? 0 to infinity e power minus st f dash of t dt. This is already a derivative of f of t. So if I do integration by parts, this will be e power minus st times f of t from 0 to infinity minus s times 0 to infinity e power minus st f of t dt. Are you okay with this? I did integration by parts, so I integrated this function for which I got f of t. That is like saying integral of f dash of t dt is f of t. That's the definition of integral, right? So I have f of t, and then I have to differentiate the other function with respect to t. So I would get s as a parameter, e power minus st, and I'm writing s outside. Obviously, s doesn't depend on time. So this is the remaining integral. What is this? That is the Laplace transform of f of t itself. So we are getting Laplace transform of the first derivative of a function is equal to, if I apply the upper limit, I get e power minus s times infinity times f of infinity. In order to say this is 0, what is the condition? To say something at infinity multiplied by e power minus s times infinity is 0, practically what is required? Suppose f of t grows with time, it is increasing with time. You are multiplying with e power minus st, but you want to say that this product is 0 when time goes to infinity. So what is the requirement? This is growing, this is reducing.
That it reduces faster than it grows.
The implicit requirement is f of t grows slower than the, or yes, slower than e power minus st decays to 0 as time increases. When we use Laplace transform, an implicit assumption that we make is that this condition is true. If this is not true, there is no way for us to evaluate this quantity. So it's implicit, okay, implicitly assumed. Minus e power minus 0 times f of 0. And then minus s times Laplace transform of f of t. By making this assumption, we are setting this to 0. This is 1. This is given initial condition. So when I differentiate, I'm not getting a s, I should be getting minus s. So this will be plus. So the result is the Laplace transform of the first derivative is s times the Laplace transform of the function, or s times L of f of t minus f of 0. What is an initial value problem? Something an ODE in which you know what is the condition at time 0. So this is always given as the initial condition. And based on your systems dynamics or control systems or circuit theory knowledge, you are almost ready to say where this is headed, which is to solve the ODE. And let's try doing that, okay? So this problem set 6.2, problem 2, very easy problem. dy over dt plus y equal to 0 and y of 0 equal to 1.5. A very simple problem. You can do the analytic solution, right? E power minus t is the solution. Not a 1.5 times e power minus t is the solution. But let's use it to illustrate the procedure. So to solve an initial value problem, which is this, step 1, obtain the Laplace transform of the ODE. What I'm writing here is applicable for any order of ODE. It can be a second order, third order equation, but we are illustrating it on a simple first order equation. So we would have Laplace transform of y dash of t plus Laplace transform of y of t equal to the Laplace transform of 0, which is just 0. The reason I write that is you could have some function here. You could say this is equal to g of t or something. So what is Laplace transform of y dash of t if you use this result? That is s times the Laplace transform of y of t minus y of 0 plus the Laplace transform of y of t equal to 0. So I have, what do we have here? S times L minus this number, which is just 1.5 plus L we have here. So this is nothing but S plus 1 times the Laplace transform of y of t minus 1.5 equal to 0, or the Laplace transform of y of t equal to 1.5 divided by s plus 1. Step 2 is to rearrange and get Laplace transform of f of t equal to the right hand side containing terms of s and other constants. So like we rearrange the 1.5, which is a parameter like the initial condition, and we have s plus 1. In a more complicated ODE, there could be more terms, but in essence, the process is this. Step 3, inspect the Laplace transform of f of t and determine which function f of t could have the obtained right hand side containing the s terms as its transform. That is, what function would have a transform which is this 1.5 divided by s plus 1? That is the question. The textbook uses the term inverse Laplace transform. I don't directly use that term because it's not so much a process through which you obtain the function from the inverse transform. It's more about inspection and fitting a pattern. if we talk about Fourier transform, the forward operation and the inverse operation are actually defined. It's an integration operation. But in here, it's more about a guesswork or lookup table. From the table, you have to say what is f of t. Okay, so we'll put it like that. So if you have this, which function has a transform 1 over s plus 1? Or which function has a transform 1 over s minus a? E power at, right? That's the first thing we saw. So this is like saying, if Laplace transform of y of t is 1.5 times or divided by s plus 1, this implies y of t is 1.5 times e power minus t, which is what you would get anyway from the variable separation exact solution. I would refer you to figure 116, which summarizes this solution process. So we did only the first derivative, right? Of course, in a ODE, the order need not be 1, it could be higher order. So we want to quickly generalize this for second derivative, third derivative, nth derivative, and so, right? So we'll start by doing it only for the second derivative and then take a generalization from there. So the Laplace transform of f double dash of t would be, again integrating by parts, I would have e power minus st f dash of t divided by minus s from 0 to infinity plus 1 over s, and again I will have a differentiation, so minus s 0 to infinity e power minus st f dash of t dt. This is like saying e power minus s times infinity times f dash of infinity plus minus f dash of 0 divided by minus s. No, wait, where did I put minus s? Because this integration was done with respect to time of f dash of t. So there is no divided by s here. Okay. The other term is plus s times, what is this? We just saw that result. This is the Laplace transform of f dash of t. And you already know the formula for this. This is Laplace transform of f of t times s minus f of 0. We knew that result, right? So I'll have plus s times s Laplace transform of f of t minus f of 0. We know what we are going to do, but you reason with me. What is the implicit assumption made here, just like we did before for f of t? This function f which happens to be f dash of t grows slower than the rate at which e power minus st decays. With that assumption, we are setting it to 0. And this is f dash of 0 provided as part of the initial conditions. And this you have here. So we are going to write, this is s squared times Laplace transform of f of t minus s times f of 0 minus f dash of 0. So this result can be generalized easily to say the Laplace transform of the nth derivative of a function is equal to s power n, the Laplace transform of the function, minus s power n minus 1, s power n minus 1, the n minus 1th derivative at 0, minus, you can easily write this, minus and so on, minus s times f of 0 minus f of 0. So this is a result, or this result is for the second derivative, for the first derivative, are things that you, if you know, you can apply that for an initial value problem. So these could be things you put on your equation sheet for this. So as this equation suggests, every Laplace transform of derivatives, higher order derivatives, essentially involves the Laplace transform of the function itself and a polynomial in S. So if you are starting with a third order differential equation, d cube y over dt cube, for example, plus let's say some a times d squared y over dt squared, plus b times dy dt, plus c equal to some g of t. Suppose this is your ODE to solve. As part of initial conditions, you would be given y of 0, y dash of 0, and y double dash of 0. At time 0, all the values of lower order derivatives and the function need to be provided. That's what defining an IVP problem is, right? So you would use this relation. What is this term? If I give the symbol f of s equal to Laplace transform of f of t, so that I can make it shorter. First term, s cube f of s minus s squared f dash of f double dash of 0 minus s f dash of 0 minus f of 0. This is the first term, plus a times s squared f of s minus s f dash of 0 minus f of 0. That is second term, plus b times s f of s minus f of 0, plus c, what is c times y? C times y equals g of t plus c times f of s equal to, let's call it g of s, the Laplace transform of the right side. You have to rearrange this to get something of the form f of s equal to. So that's what we mean by reducing a differential equation to an algebraic problem. So f of s equal to the right side, and then use the lookup table to come up with which function of time would lead to this Laplace transform. So I'm changing it over there, I'll change it here. Okay, so again, this is something you would do in control systems in circuits. You're solving for current or voltage waveforms or displacement, those kind of quantities which depend on time as a function of the input. Usually, this left hand side. Where does it come from? Could be like, say for example, if I'm writing mx double dot plus fx dot plus kx equal to h of t. Where is the right side coming from? It's basically application of Newton's law for the object that you call your system. It could be a spring or a block. It could be a block, right? And the right side, so this comes from some kind of basic physics, like a force balance. And the right side is called the input, the waveform that you use to drive your system. And then what you want is x of t, which is the output. For a driving force or driving input, what is your output? That's always the measurement question or prediction question, right? Within this framework, within this framework, sometimes this input function may not be just a function, could be the integral of some function, could be an integral quantity. So we might say, let's say we write g of t, a function of time, is defined as 0 to t f of tau d tau. Can you give me some quantities which are integrals of time, like physical quantities which you calculate by integrating over something, over time, not something? Can you elaborate one step further? You are kind of half right, but not exactly right. Anybody else wants to kind of say what he's trying to say? So if you have a, like you are taking a video of an object in free fall, and if you have your individual frames, by calculating the change in position, you can get velocity, right? That is how you go from position to velocity. But if you have a sensor like a speedometer, so I give you the speedometer reading of my car, let's say, starts at 0, might go up to 35 for some time, then I enter the freeway, it goes to like 60, and then it stays there, and then I come down to 30, and then I'm at my home, it goes back to 0. So then if I ask you the question, how much what is the distance traveled, what would you do? S equals integral 0 to some time v of t dt. Or if I have an accelerometer set up and I give you the readings of the accelerometer, you can calculate what is the average speed or what is the speed at up to some point. You can calculate all those integral quantities, right? So if we want the Laplace transform of g of t, which happens to be an integral function of time. Remember, this integration is done over some variable which varies from 0 to the time that you care about. Okay, 0 to the time coordinate that you care about. This time could be a real number, whereas the limit is between 0 to that time. Okay. People who do controls, where do you see this often? PID controllers, how does integral control work? So it will take the error. If you apply an input, that is just based on the error, which is your whatever control parameter is minus the instantaneous square. If your input is proportional to the difference, that is proportional control. If your input is proportional to the sum of the errors up to some point, or in other words, the integral of the error from say 0 to t, this will be an integral control. Or if it's proportional to the derivative, that is PID, derivative control, PID control. Usually, you might be able to say this better than I can, but a real controller has all three elements in some proportion, right? So, okay, so how do you get this? The Laplace transform of an integral. So this would be 0 to infinity e power minus st 0 to t f of tau d tau dt. Within this integral, time should be considered like a constant, but time is really a variable, right? So how do you do integration by parts on this? Which is the easily integrable function, which is the easily differentiable function? This is easily integrable, right? This is easily differentiable. So if I want to know what is the derivative of 0 to t f of tau d tau, or I can say 0 to some h of t f of tau d tau, this is f of t h dash of t. This simple result is called, anybody has the name? I learned this in high school, so I might be wrong about the name. Differentiation under the integral sign. And if you had two functions, say g of t, or use some other symbol, h2 of t, h1 of t, this would be, or h1 of t1, no, h1 of t. So this would be f of t, h2 dash of t minus f of t, h1 dash of t. Sorry. This would be f of h2 of t, h2 dash of t minus f of h1 of t, h1 dash of t. But we don't have to worry. For us, h1 is 0 and h2 is only t. So for us, the result will simplify 0 to t f of tau d tau d over dt is f of t minus f of 0 times 0. So this goes away. So it's just f of. So I would write this e power minus st divided by minus s power minus st. Wait, this is the easily integrable function, yes. Multiplied by 0 to t f of tau d tau minus 0 to infinity plus 1 over s e power minus st f of t dt. I have to apply limits 0 to infinity. Yeah. Let me rewrite this. I think I made it a little cluttered. So 0 to infinity e power minus st 0 to t f of tau d tau equal to e power minus st divided by minus s 0 to t f of tau d tau, and this has to be applied between t equal to 0 to t equal to infinity plus 1 over s 0 to infinity e power minus st. What is the derivative of this? So I'll write d over dt 0 to t f of tau d tau. So this is e power minus s times infinity 0 to infinity f of tau d tau minus the lower limit is 0 to 0. What is 0 to 0 f of tau d tau? That's just 0. Doesn't matter what f is. So lower limit we don't have to worry. Divided by minus s plus 1 over s 0 to infinity e power minus st. This is nothing but f of t dt. What is the implicit assumption here? How will you state that assumption? You have ultimately you're going to set this term to 0. E power minus s times infinity is 0, but here is multiplied by 0 to infinity f of tau d tau. How will you state?
It's faster than the tau function will grow.
There is no decay here. It's just a summation. Integration is a summation. When you plot the signal in time domain and you have a signal like this, and if you are integrating it from 0 to infinity, that integral will be a finite only if the area is finite. If your graph goes unbounded, keeps on increasing, this integral will never exist, will diverge, right? So with the assumption that f of t is finite width, after some time it has to decay to 0. It can't be a signal that forever keeps on increasing. That would make this integral goes up. With that assumption, you can say 0 to infinity f of tau d tau is finite, which implies e power minus s times infinity can be 0, and this whole term can be struck out. So we have the Laplace transform of 0 to t f of tau d tau equal to 1 over s, the Laplace transform of f of t. So the book doesn't have any examples on integral differential equations, meaning you have a function, let's say like d squared y over dt squared plus a dy dt plus by of t equal to 0 to t some g of tau d tau. Usually these type of problems occur. Anyone has encountered these in your research? I mean, of course, it appears in control systems, in signal analysis, wherever you have a switch or a capacitor that can act as a time delay. And also in some aspects of radiation physics. I remember studying this long time back, but right now I'm not able to place an example to tell you. But anyway, if you are going to solve this ODE with initial conditions, let's say y of 0 and y dash of 0 are given. What is our first step here as we did before? So it is always the steps that I provided will remain the same. Step 1, take Laplace transform of both sides. Step 2, rearrange to get f of s. Look up the f of t, which will lead to the Laplace transform to be f of s. This is the procedure always. Whatever order of differential equation, whether it contains integral terms or not, this still remains the same. Okay. So we would write s squared f of s minus s y dash of 0 minus y of 0 plus a times s f of s minus y of 0 plus b times f of s equal to, this is 0 to t g of tau. So this we will write 1 over s g of s, where g of s is known because f of g of tau is known, so g of s is. So let's maybe do like a simple example. Okay. Let's say we have d squared y over dt squared plus y equal to 0 to t e power minus t e power minus tau d tau. And we'll do y dash of 0 and y of 0. I'm just making up this problem because I couldn't find a suitable example. Okay. So this will be s squared. I'll call this y of s minus s times y dash of 0, which is half, minus y of 0, which is 1, plus y of s, which is the transform of y. So this is step 1. Take the Laplace transform of both sides. Equal to 1 over s, the Laplace transform of e power minus t. Look at this and tell me if this makes sense to you. Once you carefully write it in this form, 0 to time of some dummy variable inside, a function times d tau. Whatever that function is, take the Laplace transform of that function. So this would be y of s times s squared plus 1 minus s divided by 2 minus 1 equal to 1 over s. What is Laplace transform of e power minus t? We saw it at the start of the class. S plus 1, right? 1 over s plus 1. 1 over s plus 1. So you will have y of s equal to 1 over s squared plus 1 times 1 over s times s plus 1 plus s divided by 2 plus 1. Your real headache is actually now. You need to take the inverse of this or get the inverse of this. Do you see where the problem is? So if you take the first term, this is 1 over s squared plus 1 times s plus 1 plus s over s squared plus 1 plus 1 over s squared plus 1. With me so far?
There, S over S.
Yeah, 2.
2 squared plus 2.
Sorry?
2 squared plus 2.
No, I'm saying half of. I'm putting the 2 outside the bracket. Okay, so we have already used this result. Everybody is cool with it? Right? So that is this side. Okay. So before we deal with the first term, let's deal with the second and third because they look simpler. If the Laplace transform of something is the Laplace transform of something is 1 over s squared plus 1, obviously that function is what? I mean, you can look up table 6.1 or we did this at the start of the class. You said couple of transforms. Remember e power a t sine omega t. Sorry? Sine of t. Yep. So for your reference, the Laplace transform of sine omega t is omega divided by s squared plus omega squared. You said omega equal to 1, you get 1 over s squared plus 1. So this is like saying sine of t. And if you do the Laplace transform of cos omega t, this will come out to be s divided by s squared plus omega squared. Again, setting omega equal to 1 gets you s over s squared plus omega plus 1. So I will write the inverse transform of 1 over s squared plus 1 is sine t, and the inverse transform of s over s squared plus 1 is cos t. So we have figured out 2 terms of the solution. That is, if your solution is y of t, which is the inverse transform of y of s, the first term is to be determined, but the second term is half cos t plus sine t. Do you have a question? The first term is the real difficult one. We have to write 1 over s squared plus 1 times s plus 1 times s. If you split this into, so the denominator is a product of 3 polynomials. So if you can split this into a some partial fraction or sum of 3 fractions, you can say which 3 fractions will add up to give you this. So you have a second order polynomial, a first order polynomial, another first order polynomial. So we'll write this as plus b s squared plus 1 plus c divided by s plus 1 plus d divided by s. So you can rewrite this as plus b times s plus 1 plus c times s squared plus 1 times s plus d s squared plus 1 times s plus 1. That is equal to 1. And denominator is common on both sides, so I'm just leaving it. We'll stop with this problem and talk about it. So the way you would evaluate A, B, C, D is to compare the coefficients of s power 0, s power 1, s squared, and what's the highest you're going to get? S cube on both sides. So if we take this polynomial, you're going to get s cube up here actually in all the terms. So you will have 1 equal to s cube times a plus c plus d, right? A plus c plus d plus s squared times will have a plus b plus c plus d, and s times, where does s appear? B plus C, yeah.
I think this
Ah.
one again.
C won't be here. B plus C plus third term D, right? Squared, yep, D. And then, no, wait, I'm looking for S. Yeah, D will be there. And then constant terms. Only D. Yeah, because that doesn't contain S, so you'll have only D. So obviously D is equal to 1. You compare S power 0. You compare S power 1, you get B plus C equal to -1, and S squared will get us A plus B equal to -1, and S cube will give us A plus C equal to -1. How is this possible? So I can write C equal to -1 minus B, and I will have A -1 minus B equal to -1. So A minus B equal to 0, A plus B equal to -1, which implies A equal to -half. I might be making mistakes, but I'm trying to illustrate this. Yeah,
So if we put 0 and -1 in the equations, we can easily get C and G.
that's also correct. You can, once you set up this, since S equal to -1 will make the first and third term 0, directly you can get C. You can definitely do that because that will work for C and D. For A and B, you can follow this after you eliminate two variables. So A equals -half, which implies B equal to half, which implies C equal to -3/2, and D is already 1. So that term becomes -half plus half So you have minus half s over s squared plus 1 plus half 1 over s squared plus 1 plus c is minus 3 by 2, 1 over s plus 1, and d is 1 over s. So the inverse of this would be minus half cos t plus half sin t minus 3 by 2 e power minus t plus what is 1 over s? 1. So I have a minus half plus half, I have a plus sin t. So my solution finally is minus half goes away, 3 by 2 sin t minus 3 by 2 e power minus t plus 1. So this is the final solution. So we have covered roughly up to section 6.2, from beginning to 6.2. We'll continue in the next lecture. Okay. So I have about 5 minutes. I wanted to talk about the rest of the course. So we had the exam and we are here today, November 6th. We had also mentioned that there is a FFT mini project, which I originally said is due next Monday, but I will push it to November 13th, that is next Wednesday. What I wish to provide some of you who don't have access to a laboratory is like a time series table on which you can try your FFT program or DFT program. Okay, I will talk to my students and maybe even Alison can get us a time, some signal as a function of time, which you don't know what the signal is, but you're going to do a DFT and frequency analysis on that. Okay, so this is going to be due next Wednesday. It's a relatively simple exercise of writing a for loop and putting in a formula for DFT, which after your project 1 should not be that difficult. Project 2, I want to remind you that we will have class presentations in the last 2 lectures on December 2nd and 4th, which is the last 2 lectures after Thanksgiving. 4th is the last, or I think the last day of classes. So we'll be having that lecture. So we have a class of 16, 8 presentations on each day. And I gave you example slides. So I refer you to the lecture that was on October 21, where I went over 3 examples from the past for you to get some idea. What I would suggest you do is think about a problem and try to prepare like a 1-page summary with the equation that you would actually solve and quickly show it to me so I can give you some feedback and tell you if this is good or think again, something like that. So I encourage all of you to do that 1-page exercise. Initially, I thought I'll keep some credit for it, but that usually doesn't work. What ends up happening is students just like, I'll let go that 5%. They'll not adhere to that. So I'll leave it to you. Exam 3 is going to be on the topics related to Laplace transform and vector calculus. This is the Monday of the Thanksgiving week. So by Thanksgiving week, all your exams are done. All my lectures will be done. The only 2 things remaining will be the 2 presentation sessions after Thanksgiving. Okay. Coming to now exam 1, which I graded and I posted the scores scale to 20 points. In a class of 16, I could count maybe 4 or 5 students who did well, and by well I mean 85 or above, and a majority did not do well in my opinion. There are many reasons. I would encourage you to think about it, take a look at your exams, see what you did. Most of the exams are very simple. Most of the problems, especially the first problem, the last problem is an example from the book. Look at the solution and see what you missed. Think about it, and then if necessary, we can talk. Okay. I understand everybody is trying to do well in this course because it's a required course. You are all graduate students. You don't want your GPA to look bad. All hope is not lost. I looked at some of the exam two, in which the performances have significantly improved. I also eliminated the task of integration from the exam, which greatly helped, I think. So in the final, that is there is the optional final, which you can take. If you take, it will replace all the scores. But I can see a situation where many students will have a poor score on exam one and maybe better scores on 2 and 3. So what I will try to do is to turn the final into part 1, part 2, part 3. But I will still grade it for the entire exam and try to replace either part 1 score with your exam 1 score or some combinations thereof. Suppose you did extremely well in part exam 2 and 3, you don't need a boost there. I will let you replace only your exam 1 score. But you have to take the entire exam. You have to show up for the entire exam and take it. Okay. So what I wish to say is it will be brutal, like in the sense your score that you got, for especially those of you who did not get good scores. I understand it will be difficult, but I want you to stick with it and come outside the other side for what it's worth, a better student, so that you practice again and come back and do well in the final. Okay, so if you come to me, I can explain to you my grading, what my thinking, whatever comments I wrote there. I'll try to explain myself, but 99% don't expect me to increase your score. I try to be consistent for all of you. Do not come to me asking like an undergraduate student, can I get 5 points here, 3 points there? I can perhaps help you study, but I won't increase your score mostly, unless I blatantly made some mistake that I'm willing to correct. Okay. At the end of the day, I want you to be good at this special functions business. Okay. So after the exam, exam 2, I got an idea that in the exam, you derived the Fourier coefficients, left it in integral form. Maybe like a special credit exercise for those who want to earn some extra credit. A possible exercise is for you to write a computer program in which you calculate the Fourier coefficients for problem 2 and problem 3. You write up, one involves Bessel function, the other involves Legendre polynomials and an integral of those. You could write a routine that numerically computes the integral and gets the Fourier coefficients A0, A1, A2, everything. If you do that, you would have actually learned much more than what that exam tested. So for those who at some point in this class feel like if there is an extra credit exercise, I would determine how much credit to give, but here is the extra credit exercise. Implement computer programs to calculate the Fourier coefficients that appear in problem 2 and problem 3 of the exam. Okay, so it will be a very good exercise to tell you. I'm telling you. Lastly, exam 3 is going to be an easy exam in the sense the topics are pretty light compared to what we already saw. So I really hope you would practice these Laplace transform stuff and score well. Okay. I am somewhat concerned about 3/4 of the class, or at least 1/2 of the class, scored less than 50%. But I think if you do all these suggestions, we can definitely improve the class average. Okay. So I'll see you on Monday. Thank you. Yeah. It will be at least a week.